So I'm happy to introduce Jack Jeffries, who's been at CIMAT this year and is now in Utah and will be at Nebraska next year, who's going to talk to us about applications of p-derivations
Okay, great. Yeah.
and related material. I didn't have your exact title in front of me.
Oh, it's. I think it's the one on the
applications of p-derivation. Okay, I do have it in front of me actually.
Great. Well, yeah. Thanks a bunch for the introduction. Thanks to the organizers for organizing the seminar and for inviting me to speak at it. It's nice to see those of you whom I can see, and for everyone else who's attending, it's nice to have you here with me wherever here is. So. Yeah, well, let's do some math. So in the first half of the talk, I want to mainly focus on introducing this notion of p-derivation. And before we do that, I want to review some stuff about derivations. So if derivations are not familiar, or if they are familiar, either way, I want to talk about some basic aspects of derivations. And if some of the things are very familiar to you, then that's okay. Bear with me because I want to contrast them with this other setting, this other notion of p-derivations. So that's the goal for the first half of the talk: review derivations and introduce or review p-derivations if you happen to be familiar or an expert or whatnot. Then in the second half of the talk, we'll try to get to some new stuff. So there I want to try to apply this notion of p-derivation to a couple of different questions in commutative algebra. And this will be based on joint projects with Mel Hochster and Anurag Singh separately. Okay, so, whoops, here we go. Okay, derivations. So let's just start by recalling the definition of a derivation. Okay, a derivation on a ring R is a map that we might often write with this partial symbol from the ring to itself, such that, well, the way I want to write it is that there are two rules, one for breaking apart addition and one for breaking apart multiplication. Okay, and I'm gonna copy this for later so I can reuse it. This is the one advantage of having one of these things as opposed to a blackboard, I guess. So, whoops, there we go. Okay, and condition one, this is just saying that these are Z linear or additive maps. And sometimes the derivation will be linear over a larger subring. In particular, the kernel of a derivation is a subring, and it'll be linear over that. But sometimes I'll just say a linear derivation, okay, just as a heads up for that. The prototypical example is just partial differentiation. So, oops. So if we have a polynomial ring over some other ring A, then partial differentiation with respect to any of these variables, formal differentiation, you might say, since there's no limits or anything. Okay, this is the prototypical alinear derivation. And at least in the calculus case, rule 1 and 2 has some roll product role name in Calc 1. So I want to make a first simple observation about these things. So if R is a ring that's not a field, then in general, we can't undo multiplication with multiplication. Okay, then that's what it means to be a unit, more or less. But we might be able to try and use derivations to undo multiplication. So let me just write down an example of what I mean by that. So A is a ring of characteristic 0. We're again looking at a polynomial ring over A. And F has xi adic order exactly n. So first, let's give it positive order just to make it a little cleaner. Then this formal differentiation decreases the xi-adic order by exactly 1. And we can just see this by looking at what it does to monomials, or we could try and scrape up an argument using the formal properties. But these can sometimes undo multiplication without having to invert, without having to pass to a localization and lose part of our spectrum. Okay, so I want to think of them as maybe being useful for something like this. Great. So these things are linear maps, but let's put this here just so we can remember the rules. These things are linear maps, but also they collect together linearly. These conditions 1 and 2 are linear by their nature. And so, oops. So let's say these conditions 1 and 2 are linear in partial. And this has a couple of nice consequences. The set of A-linear derivations is then an R module by post-multiplication. Okay, so what do I mean? If you replace delta by R delta, then you're going to equally preserve these equalities 1 and 2. Okay? And the things on the right-hand side, well, let me just say that because these are linear in nature, we can define the notion of a derivation into a module by the same rule. Okay, so as long as delta of x or y or delta x plus y is something in a module, then everything in these equations makes sense. Okay. Great. Okay, and when we start to think of this as derivations as something going into modules, then there's a universal object. And so this is sort of following the second starred point. Okay, so this is going to be my universal object, and that means that for any derivation into a module, there exists a unique linear map from this universal object that makes this all commute. And another way of thinking of this, once we start to group these things together, is that once we fix an M, then there's a bijection between the derivations and linear maps coming from this, this omega thing. Oops, that's not the thing. And there's an isomorphism like so as our modules. And I should write down the name because I'm going to say it. Okay. Right, say the name, Euler differentials. Okay. Good. So let me mention a couple of examples of rings and the collection of all derivations on them, or collection of all a linear derivations on them. For a polynomial ring over A, we've already named all of the derivations. Well, we named all of the generators, and then we said that it's a module that's generated by generators. Yeah, let me write on this line. Okay, so any A-linear derivation is uniquely a sum of post multiplications of these partial derivatives. Oops. Okay. And let me take something that's not a polynomial ring. And so this nice hypersurface, I want the characteristic to be not 2, maybe K is a field. Hopefully we all agree that this is a nice hypersurface. It's not regular, but many other nice things that we can ask for a ring are satisfied by this. Okay. And let me write down just a generating set for the derivations. Okay, you need a couple lines. So there's this first Euler derivation, as we might call it. This is a derivation that for any homogeneous element just acts as a scalar multiplying by its degree. And then there's these causal looking derivations. Okay. And the main thing that I wanted to note about this set of derivations is that among these, none of them decreases degree or M-adic order and the homogeneous maximal ideal. So, okay. So there's nothing that works exactly in the same way as ddx that we saw before that we kept decreasing order. Okay. And there is a classical theorem behind this that I want to state just because I think it's pretty nice. So it more or less characterizes when we have something like a ddx. And I think different sources might attribute this to different subsets of people, but at least in Matsumura, this is attributed to Nagata, Zariski, and Lippmann. If we have a local ring of equal characteristic 0, and equivalently contains the rationals, take something in the maximal ideal, and the actual condition is that there's a derivation that takes x to 1, then the completion splits off as a product, more or less. Formal product, I guess is a nice way to say it. And I'm going to use the same symbol x. In the completion, the image of x generates something that behaves as a formal parameter. Okay. So if there's something that looks, a derivation that looks like ddx on a ring, then, well, this only happens if we have some sort of formal regular parameter. Formal regular parameter. Okay. Great. So those were a few things I wanted to recall about derivations. Some of us are probably less familiar with p-derivations. So let me start with the definition. Okay. And this is a notion that was independently defined by Joyal in the 80s and Guillaume in the 90s, with different terminology for in the two cases. But okay. The p is a prime number, of course. And R a ring. A p derivation on R is a map from R to R that satisfies axiom functional equations that look like those for derivations in some sense. There's also this condition 0. The analogous thing holds for derivations, follows from the other two, but here we should pose it separately. Oops. Good. And, well, whatever the details I'm writing, there's a formula for breaking apart addition and a formula for breaking apart multiplication. And I'm going to gather these for reuse. Copy. Good. Okay. So there are a few things to unpackage, even just looking at it. So binomial coefficients are integers, and the denominator in a binomial coefficient p choose I, where I is in this range between 1 and p minus 1, does not have p as a factor. Okay, so as integers, we must have that this fraction is, we can do this division in Z. So for I between 0 and p. Okay, so it looked like we were trying to divide by integers, but not really. Oh, gosh, yeah, and in the chat, it was noticed the writing is small. That's an I factorial. Thanks. Thank you. Okay, and this makes sense in any characteristic. Great. Another thing to think about in condition 1 is that these are, since it's not just delta x plus delta y, these are not additive functions. Furthermore, these conditions are not linear in delta anymore. Let's see, do I want to copy and paste yet? No, let me keep it here so we can just see it. Okay, so in Formula 1, we're trying to add something on the right-hand side that is not a delta of something. In Formula 2, we're trying to multiply together two deltas of somethings. Okay, so these are so we cannot define a p derivation into a module. So for M and R module. We can do it for M and R algebra, but not for a module. And there is no analog of Euler differentials because there is no derivation functor from R mod to represent. Okay, so already there are a couple of things that are fundamentally different about these types of equations. So the next thing I want to do to try to get a sense for them is to try to discuss what the axioms mean. Where do these equations come from? Oh, and I'm going to abbreviate p derivation like this. So maybe I should say that in case that's unclear. Yeah. If we have a function that satisfies these axioms, basically the point is that we can package this together to form. Sorry, were you waving, Carl?
Yeah, sorry. I just want to get your attention.
Okay.
But there is a question in the chat.
Oh.
Derivations form a reduced Lie algebra if P is 0 in the base ring?
I see. This I don't know. I'm not aware that they do. Perhaps someone in the chat can can say if they know for sure. But to my knowledge, that they don't.
Well, isn't what your comment? You're saying that they're not close in addition.
Yeah, that's right. Yeah, they're not close under addition. Yeah. So okay. Yeah. So to my knowledge, they don't. Yeah. That's great. So if we have a p derivation, the point is we can make a ring homomorphism out of this, or one point is that. So. So if we have a p derivation, the map from R to R given by this formula is a ring homomorphism. Okay, and one can check by just plugging in the rules. Okay, and once we believe that, then it's clear that when we go mod p, we're just left with x goes to x to the p. So this diagram commutes. And such an endomorphism is elliptic Frobenius. And I'll abbreviate that as LOF. Moreover, if P is a regular element, maybe I should take this to the next page. Now I'll make this fit. Then this yields a bijection between P derivations and Lifter Frobenius. Okay, so for any Lifter Frobenius, we can solve delta x is phi of x minus x, or phi of x minus x to the p over p. That's a P derivation. We'll be most interested in this case where P is a regular element. So let me just make as a note of where we're going. Oops, not that. And we'll mostly be focused. On this case, so locally in mixed characteristic. Okay, so let's see some examples. On the integers, for any p, the identity map on, well, the Frobenius on Z mod p is the identity. So the identity map on Z is the unique Lifter Frobenius. And solving for delta as above. This is the unique p-derivation. And let's just throw in a few numbers just to get a sense of this. 1 minus 1 over 3, okay? 2 minus 8 over 3, good. And so on. Okay. In any case, not linear. On the p-adic integers, the story is very much the same. So again, when we go mod p, we have fp, so the identity is unique lift of Frobenius. And there's a unique p-derivation given by the same formula. This formula. I want to just give a short name to a setting that that generalizes the p-adic integers for the purposes at hand. Okay. So I'm going to follow the notation from Sayre. If we have a strict P ring is going to be a complete DDR with uniformizer P and perfect residue field. Then V admits a unique lift of Frobenius and unique p-derivation. So I'll often just call for strict P rings, and you can think of the p-adic integers. Right, and then the next example, it's more a construction. If we have a p-derivation, we can extend it to any polynomial ring. So if we have a ring A with a p-derivation delta, then if we choose whichever images we like for the variables, there's a unique extension. Such that is an extension. Okay. We send the variables wherever we like. For concreteness, we might prefer the one where we send the variables to 0. We'll just call that the standard extension. Or in the case A is a strict P ring, we'll call it the standard P derivation because there's a unique thing that is extending. Okay, so this will uniquely specify a P derivation. What does it look like? So we collected a little bit of terminology and whatnot, but again, we can make this very concrete. over the integers, let's say, the standard p derivation. Okay. Well, it's maybe easier to think about in terms of the lift of Frobenius. The lift of Frobenius is sends variable to, or sends something to its pth power plus p times the p derivation. So the variables go to their pth powers. So this corresponds to lift of Frobenius psi with variables go to their pth powers. Okay. And then we take that, we subtract the pth power, and we divide by p. And so it's the p derivation, standard p derivation is just given by this formula. I like to call this the freshman's nightmare, right? The freshman's dream is that the two things in the numerator are the same. This is exactly measuring the failure of the freshman's dream. Okay. And I guess in some sense, we can think of every p derivation as a freshman's nightmare. Anyways, all right, let's copy these axioms again. We haven't seen them for a little bit. I want to concretely put them to use. We'll leave the examples for a second and see something that they do. So say R is a ring with a p derivation delta, and again, I want to assume that p is a regular element on R. Then if f has p-adic order exactly n, and I do want to assume that it's positive, then, well, I shouldn't write the word then. Okay. The p-adic order is decreased by exactly 1. Okay. And let's prove it just to try out these axioms. Okay. So one thing to note about the axioms is that if we take an integer, well, we know for any p derivation, we know that 1 goes to 0. If we plug in the sum of two integers, then formula 1 tells us that we get some other integer coming out. So this restricts to a p derivation. Any p derivation restricts to a p derivation on z. So. And so if I wanted to evaluate delta of p, then I could just use the explicit formula we wrote down before. P minus p to the p over p. Okay. We canceled the p. I'm going to paste the axioms again, just for reference. Okay. All right. So let's note that, well, we can write f like so, where g has p-adic order exactly 1 less. Okay. And let's just use axiom 3. And we'll collect the coefficients that go with delta G. Okay. Well, those collect to P based on what we just evaluated before. Okay. Now, let's copy again. Hopefully, oh no. Okay, good. Okay, so be it. Okay, so first we'll deal with the case when n is equal to 1. Okay, we want to consider the p-adic order of this. And I'm just going to write p-adic order in purple. Okay, so here we've got a 1. We've got now a 0 and a 0. And so the p-adic order is 0, which is what we want. And n is greater than 1. And paste again. We've got a 1. We've got an exactly n minus 2 by induction hypothesis. Okay, so we're inducing on n. And here we've got p times n minus 1, which by a famous property of primes is greater than n minus 1. Okay. Primes are greater than 1. And so the p-adic order is exactly n minus 1. Okay, so yeah, so what is this?
Jack, there's a quick question.
Yeah.
Is the p-adic order really well defined away from Z, even if P is regular? Maybe not prime.
Well, so any element is well, so here I'm assuming that F is something that has a p-adic order. P is in the smallest power of P. Actually, why don't let me just go ahead and assume that P is prime in R. Yeah, let me just simplify and say P prime in R. Okay, yeah. Good, thanks. Okay, and so since this is something that decreases p-adic order, we might think of this as something like a pure derivative by P. So. Okay, good. Let me give a couple more examples where we may or may not have such maps. For a semigroup ring, the standard lift of Frobenius preserves the semigroup ring, restricts to a ring endomorphism there. And so the standard p derivation restricts to a p derivation on the semigroup ring. Okay, so there are non-regular rings that admit p derivations, but it's a special condition to admit one, and so it follows from a so this is not exactly stated, but it follows from a result of Zdenovitz. So for V a strict P ring, again, if we have a homogeneous polynomial, of degree greater than the number of variables, and when we go mod P and mod F, we get something normal. Then this hypersurface does not admit a P derivation. Okay, so normal hypersurfaces of high degree do not admit these things. Let's see. So I want to make a quick piece of terminology. If we have a map from R mod P to the N to R mod P to the N minus 1 that satisfies the same axioms from before, the P derivation mod P to the N. And if we have a P derivation on R, then this will induce a P derivation mod P to the N if P is a regular element. But from work of Zdenovitz, one can say, and I can test in a relatively concrete way whether a hypersurface admits a P derivation mod P squared, at least. And then there exists a P derivation mod P squared on the hypersurface cut out by F, if and only if the standard P derivation on V of X ends up in the ideal generated by the pth power of the partials. Sorry for squeezing this in here. Ideal generated by pth powers of partials. And I wanted to mention this since I will call on this later. Okay, so sometimes they do exist. They always exist on polynomial rings, but this this may be a special condition to admit such a thing, based both on the example number 6 above, and maybe perhaps in analogy with Nagata's Zariski-Lippmann result on derivations. So I do want to say just a few words about how where these show up where these have shown up in mathematics.
Jack, would now be a good time to take a quick break?
Sure. So either now or just 2 minutes about where these show up, because then
Okay.
I'll get onto something else when we come back.
Okay.
So in the 80s, Joël introduced these to study bit vectors in a concrete way. So a ring with a p derivation admits a natural map to its ring of p-typical vet vectors, and one can make a nice construction for them using p derivations. So that's one thing that one sees from his work. So William has used p derivations in a lot of different projects for a lot of interesting results. So when he reintroduced these in the 90s, he used these to construct an arithmetic jet space. Which is a space that, modulo some technical conditions, represents the functor of p derivations from algebras to sets. There's some technical issues to deal with gluing, but in any case, one can construct some version of a jet space and use the intersection theory on these to give explicit bounds on the number of rational points on curves. Recently, Bott and Schulze have applied p derivations. So let me say that certain data, including the data of a ring with a p derivation, p derivation is a D perfection of a perfectoid ring. And starting from there, I've gone to unite many different cohomological theories based on this idea. This is the notion of prismatic cohomology that I'm referring to. Also recently, William and Lance Miller connected arithmetic jet spaces to perfectoid spaces. Let me just say that out loud. And oops, that's not helping. And also various authors, including Borger, Buiem, and Manon, have proposed that that the data of a ring with a p derivation, or even better, the data of a ring with commuting p derivations for all primes p, should be thought of as a reasonable model for the field with one element. So I'm not going to go into any more of those. Instead, yeah, now I think it's a good time to take a break. Yeah, so now that we've seen these p derivations and seen a little bit of their basic properties, let's see if we can take them out for a spin. Okay, so let me ask a question that I think many of us can answer in under a relatively mild hypothesis, or a hypothesis that we often find ourselves living under. Okay, especially since the answer is written above the question. So over a perfect field, to find the singular locus of a K-algebra, we might use the Jacobian criterion. So I want to just set up some notation to recall what exactly I mean by this. Given a ring and a polynomial ring over A, and some elements, then we've got what we need to fill in a Jacobian matrix. Okay. And K is a perfect field. And we have some algebra that's presented by an ideal of pure height H. Then the singular locus of R is cut out by the H by H minors of the Jacobian matrix, which maybe we'll think of as a matrix with entries in R. Just take everything by by. Okay. One useful way to interpret this, both for its own sake and for generalization, is in terms of these Euler differentials. And the key point is that the Jacobian matrix presents the Euler differentials. And so then minors of the Jacobian matrix are just fitting ideals. Ideals of minors of the Jacobian matrix are just fitting ideals of the Euler differentials. Okay. And then using fitting ideals to characterize free modules. I'm going to switch to the regular note locus because I don't want to just negate or take the opposite of both sides of what I'm going to write down otherwise. Then we can interpret this, the Jacobian criterion, as saying the regular locus is the locus where the Euler differentials, the module of Euler differentials, is free of the, and I know I could write the actual rank and dimension of R, but I'm just going to say of the correct rank. Okay. And the reason I want to do that is that to also recall that if we replace K by an arbitrary ring A, then the Jacobian criterion has a generalization. To detect the smooth locus of the map from A to R. And I don't want to bother writing down the proper statement, but just the point is that the smooth locus is the locus where this holds one writes down the correct version of correct, and one also needs to insist that the map is flat. And so map is smooth if and only if it's flat, and the Euler differentials locally have the correct rank and are free of the correct rank. So that's well and good. But smoothness is not non-singularity. And if you're not familiar with the notion of smoothness, even if you are, I'm gonna do the same example for you as well. this is an example where V is again a strict P ring, perhaps the p-adic integers. This is not smooth over V. Then, there is no then. This is an example of something that's not smooth, but is regular over V. If we think of smoothness as flatness with geometrically regular fibers, fiber over PV is not regular. But R is regular. And so this is an example of the difference between smooth and regular. And let me just write down the Jacobian matrix over V. So the Jacobian matrix for this, thinking of our presentation as a presentation over as a V algebra, is this. The Jacobian criterion for ideals of minors would tell us to look at the ideal of 1x1 minors or the ideal of entries. So V of the ideal of 1x1 minors is V of xy, and that also picks up P. Let me throw that in there too. So it contains a unique maximal ideal. So unique maximal ideal. Okay. But that maximal ideal was really too generated. So even that one, at that one, we're regular. Okay. What question am I getting at? How do we find the singular locus in mixed characteristic? So we know how to find smooth locus over something, if we, whatever base we choose, but I don't want that, I want the singular locus. And from the point of view of the Jacobian criterion in terms of these matrices, maybe one thing we might choose to blame about such a matrix is that there's a regular parameter in our presentation that we can't differentiate by, namely P. So let's try to also differentiate by P. So let's start with a ring with a P derivation. Right, so this is supposed to be a similar setting to the setting of the Jacobian matrix, but we also have a P derivation. And take any P derivation that extends delta. Then for whatever tuple of polynomials, there's this, let me give you another recipe for a matrix. And maybe the only unexpected thing is that I'm raising these partials df dxi's to the p. Okay. Okay. So if we have a strict P ring, and let's just forget that it's about, any actual ring, the p-adic integers works. And we take a presentation by an ideal pure height H, and delta tilde a P derivation dx. Let me write the word any here. Then I want to compute the singular locus. So the first step is to separate the sheep from the goats. Okay. Primes that do not contain P are well behaved. Because when we go to the localization, we're just an algebra over the fraction field of V. So that's basically just characteristic, equal characteristic 0, classical Jacobian criterion. We use the same formula, the same matrix. Okay. Okay, and then for the goats, we take the mixed Jacobian matrix. Let's see, does this compile? Give me one of those. Okay. Let's see an example. Okay, let's go back to this and consider the standard P derivation on the polynomial ring in X and Y. Then if we wanted to compute this mixed Jacobian matrix, there's one calculation that we haven't done that we have to do. Okay. And remember, standard Lift of Frobenius means freshman's nightmare. So here I'm just doing that. Okay. And it's not so hard to collect together. Write out explicitly what we get. Okay. So, oops, nah, I want this. Okay. So our mixed Jacobian matrix has that minus x to the p minus y to the p. And we want to intersect with, we want to intersect with v of p. And so we only want the primes that contain these entries and p. Well, this is a multiple of p. Okay, so there are no primes in the singular locus that contain p. likewise, from the other Jacobian matrix that we looked at before, there are no primes that don't contain P in the singular locus either. And so the P derivation sufficed for this criterion to cast out the sort of the missing, what we might think of as the missing piece. Okay, let me just say a little bit about, and since I kept mentioning these Euler differentials, there are no Euler differentials for P derivations. But this, but perhaps this criterion analogy with the classical Jacobian criterion suggests that the co-kernel of this other matrix might be trying to tell us something. And in fact, the co-kernel of this matrix, I want to think of it as a matrix over R mod P. Right, we were only interested in primes that contain P anyways, so this, geometrically, we're not really losing anything. Okay. Well, the co-kernel of this matrix is independent of the presentation. Presentation of R as a V algebra. And the choice of this P derivation, this extension of the P derivation to polynomial ring over V. So, and the point is I'm trying to compare this to the co-kernel of the other thing, which is independent of presentation and represents a functor. Okay. Likewise, this co-kernel represents a functor, and I don't want to get into the details, but I'll say it represents a functor with similar properties to derivations. But also similar to P derivations. Okay, so there's a little bit of a portmanteau going on here. This was also, I should say, partially inspired by Neil Epstein gave a talk about perinormal domains, and then the prefix kind of stuff. So, okay. So so sort of the idea that motivates this is that a P derivation is the missing derivation that can actually decrease p-adic order. And this idea, we used this earlier to characterize symbolic powers. Okay. In analogy with the Zariski-Nagata theorem, and this was joint work with Alessandro De Stefani and Elisa Grifu. Okay. So at least using a P derivation as a missing derivation, there are at least a couple of situations where this can be made to work in the context of presenting things over a polynomial ring. So this is in polynomial rings, we always have P derivations, and sometimes we can use them like missing derivations. Okay, I want to now switch to a different application that uses p derivations in a different way. And yeah, I'll need a little bit of notation. So we're gonna think about some specific rings. And those of us who were able to attend Anurag's talk 3 weeks ago will remember these rings. Okay. Well, first I want matrices. Okay. So I'm just gonna set up some notation for generic square matrix, the symmetric matrix of variables, alternating matrix of variables. Okay. And each of these has a determinant. Well, we'll tweak it a little bit in the alternating case. So each is a recipe for an interesting hypersurface. Okay, I think that notation's easy to remember. I'm just gonna go here. Let me know if you forget. So I want to think of each matrix as a recipe for a classical determinantal hypersurface. Okay. I don't want the determinant of an alternating matrix. Of course, I want Spafian instead for an even sized. So all of these will be one of these at some point. And each of these hypersurfaces naturally embeds as a subring of a polynomial ring. And so if we take the product of an n by n minus one matrix times an n minus 1 by n matrix, then we get an n by n matrix, a generic n by n matrix of rank 1 less. And that's the recipe for this embedding. So the entries of X go to the entries of the product. And similar embeddings for generic symmetric or alternating matrices of rank 1 less. Okay. And here omega is the standard symplectic matrix. Even better, if A is a ring with an infinite unit group, then each R is the invariant ring of S by some group action. By a classical group. Okay. And each of these invariant, classical invariant, or classical determinantal hypersurfaces has good properties regardless of the characteristic. So okay, so these are not smooth or regular, but as far as singularities go, they're good singularities. Okay, and I want to emphasize regardless of the characteristic. Field of characteristic 0 or P, or mixed characteristic DDR. There are Cohn-Macaulay. Oops. Call. There we go. Pseudo-rational. And other good things we can say. And these good properties, we can deduce them from different techniques, very different sets of techniques. So one family of techniques, standard monomial theory or Hodge algebra theory. And many names go here, but I'll put down Deconcini, Eisenberg, Berchesi. And for example, this technique allows us to see that these are invariant rings by the same group action in regardless of the characteristic or regardless of the base ring. And those of us who saw Craig's talk on the other side of the planet on Tuesday, we're probably familiar with another technique. In characteristic 0, these groups admit averaging operators, so they're linearly reductive. So these inclusions into the polynomial ring split as R modules. Okay. And this relationship between a ring and a polynomial ring is very powerful. Okay, so these R's are direct summands of polynomial rings in characteristic 0. And so let me emphasize fields of characteristic 0. Okay. And leveraging this is a very old idea. We might, in modern language, think of this as what's going on in the first commutative algebra paper in 1890, Hilbert on invariant rings. So proofs of Hilbert and Noether of finite generation use this direct summand property. Work of Hoxer and Roberts uses this direct summand property to deduce Cohn-Macaulayness, so on and so forth. And one can even use just the characteristic 0 splitting to deduce good properties in other characteristics, characteristic B and mixed characteristic. But in other characteristics, one can see that these embeddings of R into the polynomial ring S as these explicit embeddings do not split. But R still has every quality of a singularity, or R seems to have all those qualities of singularities that we think that a direct summand should have. And so that motivates the following. So in the mixed characteristic setting, for example, over the p-adic integers, the classical determinantal hypersurface rings let's line them up again. And a little bit of a even odd distinction in the symmetric case. But otherwise, we just want n to be at least 3. It's not a very statement. These are not ducks, despite quacking like one or flapping like one or whatnot, i.e. this is the terminology from Monroe's talk. These are not direct summands of a polynomial ring by any embedding. And hence are not pure subrings, but of a graded pure subrings of a polynomial ring. And just as a remark, we can say a lot of good things about direct summands of polynomial rings, but somehow the toolkit for excluding a ring for being one is kind of limited once you, or feels like the toolkit is kind of limited once your singularities are good enough. So great, so let me just say over FP, we don't know for any of these. Whether they're direct summands of polynomial rings. I don't know a way to exclude them in positive characteristic. And yeah, sorry, I'm a little bit over time. So let me just remind you that this was a talk about p derivations. We might have forgotten in the last few minutes because we haven't seen them in a while. Okay, so what's the point? If we have an inclusion of V algebras that's a direct summand, well, let's say S has a p derivation mod p squared, and R2S splits as R modules, then R has a p derivation mod p squared. Okay. But this property we can rule out for these determinantal hypersurfaces. Okay. One can actually use this explicit criterion. Classical. Do not. So even though many of the properties of these classical determinantal hypersurfaces seem to be very independent of the characteristic. For example, the F pure thresholds are constant among primes, at least once you exclude very small ones. Then even though the behavior it seems to be very uniform, somehow it's not it's not in this way. There's not a there are not p derivations on these. And yeah, sorry for going a bit over. Yeah, thanks.
Okay, let's all thank the speaker. And you can use the, and if you have any more questions, please go ahead and ask in the chat. There is one question. What functor is, oh, those are two questions I see.
Sure.
So what functor is represented by derivations? Derivations?
Okay, sure. So actually, derivations is the functor that's represented by the cokernel of this matrix. So there's a functor from what do you call this? I don't want to underline it. There's a functor from R mod P modules to itself that's represented by the represented by this co-kernel of this mixed Jacobian matrix, which let me write like so. And let me just stick with V here. Okay, so like so. And basically it's a functor that looks kind of like derivations. They are functions from R mod P to such a module that satisfy axioms about addition and multiplication. I could write them down, or there's great demand.
Okay, and then one other question. Checksum and as what? I'm guessing as a R module.
Yeah, that's right. Yeah, so hopefully I wrote it down right the first. Yeah, I wrote it out completely the first time. Yeah, the condition is that the inclusion splits as modules over the source, and then then for sure to just say direct summoned to mean like so. Yeah.
Okay.
Very nice.
What is the singularity of these hypersurfaces and characteristic P?
So what do you mean by what is the singularity?
I'm going to have to ask F regular.
Okay, that's a good answer. I like, yeah. It's depending on what exactly one means, different. There could be different answers. One is these qualitative answers. F regular, F pretty much whatever. But also can the singular locus is just cut out by the minors of size 1 less.
Can you, Bargov asks, or can you explain roughly why the P powers show up in the mixed Jacobian matrix?
Yeah, so one, okay, so can we see? Probably not. So we got the axioms here. Let me just, so one very, very short and not convincing answer, I guess, is because of the P's in the multiplication axiom. Okay, because that's a not very strong thing, but a better answer, goodness, so many pages, is that is this consequence of the axioms.
Okay. One more question, I guess.
Oh,
Why
sure.
do hypersurfaces of degree bigger than n don't have p derivation?
Yeah, sure. So actually, the point is that if R mod P is normal, and sorry, if R admits a P derivation mod P squared, and R mod R mod P is normal, then R mod P is F pure. That's really the fact that's going into this, and then F pure implies that the invariant is non-positive.
Okay,
Thank you again, Jack.
Yes,
Thank you, Jack. Great talk.
Great,
Thank
thanks.
you.
bye-bye.
Thank you. Goodbye.
Oh, bye, thanks.